Okay, let's get straight into it today. We're looking at a paper called Uniform Discrete Diffusion with Metric Path for Video Generation.
And the model they're introducing is URSA. That's Uniform Discrete Diffusion with Metric Path.
Right, URSA.
Yeah.
And it's really aiming to shake things up in video generation, challenging the continuous diffusion models that, let's be honest, have been dominating.
Yeah, it's a big swing because, discrete models, the kind that work so well for language, they've really struggled with video, mostly because of error accumulation and just keeping things consistent over longer clips.
Exactly. But URSA's core idea is different. They're not doing that old step-by-step prediction thing. Instead, it's about iterative global refinement of these discrete tokens. Conceptually, that sounds a lot closer to continuous diffusion, right?
It really does. And to make that work, they introduced two key things. First, a linearized metric path, which gives them really fine-grained control over how they perturb the data. Second is this resolution-dependent timestep shifting. It basically lets the model scale up to longer videos or higher resolutions without needing tons of extra inference steps. Makes it much more efficient.
And then there's the versatility part. This asynchronous temporal fine-tuning strategy sounds quite clever.
Oh, it's neat. It basically lets them train one model to do a whole bunch of stuff. Text to video, image to video, even video interpolation and extrapolation, all unified.
And the results? They're pretty eye-catching. A V-bench score of 82.4 for text to video. That puts it right up there, even against some bigger continuous models.
Yeah, it's definitely a strong signal that this discrete approach has serious potential. It's not just theoretical.
Okay, so that's the snapshot. Let's unpack this properly.
Yeah.
Starting with what you call the discrete dilemma. We know continuous models, diffusion models, are king for images and video right now. Super high fidelity.
No question. But like we said, LLMs live in the discrete world, tokens. And when people tried applying similar discrete methods like autoregressive models or mass diffusion models, MDMs to video,
they hit problems.
Big problems, especially with video.
And the main issue was that coherence, keeping things looking right over time.
Fundamentally, yeah. Think about how those older models work. Autoregressive predicts one token, locks it in, moves to the next. MDMs might do more in parallel, masking things out, but once a token's predicted, it's fixed. It's non-refinable.
So local decisions that can't be revisited.
Exactly. And over hundreds of tokens, dozens of frames, those tiny errors just build up and up. You get weird visual glitches, or more subtly, objects just don't move naturally. The long context consistency breaks down.
Even with bidirectional transformers and MDMs, that fundamental fixity was the limitation.
That seems to be the case.
So URSA's insight was, if you want to compete with continuous diffusion, you need its core strength, that iterative refinement. Move away from predict and fix.
Towards refine and correct. The whole process in URSA focuses on iterating over the entire set of discrete tokens, globally, improving them step by step.
Okay, so we see why the shift was needed. Now, how did they build this refinement framework? It starts with discrete flow matching, DFM. What's that doing here?
DFM is sort of the mathematical engine underneath. Think of it like a way to define a smooth path, a probability path from pure random noise, $2.1, all the way to the clean target data, $1.
Like mapping the journey from chaos to coherence.
Pretty much. It uses a velocity field, a way to model how things should change over time. This simulates what's called a continuous time Markov chain, or CTMC, but operating in this discrete token space.
So you start with random tokens just uniformly chosen.
Yep, pure categorical noise, $6. And then the model iteratively nudges these tokens along that DFM path, guided by the learned velocity, until hopefully you arrive at the target video, $6.1.
But navigating that path, especially with complex data like video, needs really careful control. Which brings us to their first big innovation, the linearized metric path. Why linear? Why was that so important?
Precision. When you're dealing with potentially millions of tokens for a high-res video, you can't just randomly zap them with noise. You need very controlled perturbations at each step. If your noise schedule is erratic, training gets unstable fast.
Okay, so how do they achieve that precision?
Instead of just a simple time-based noise decay, they base the probability path, PTBI by the dollars, on the distance between the current tokens, X, and the final target tokens by 1. Specifically, the distance in the embedding space of the token codebook.
Ah, so the path is defined by how far the current state is from the goal state in embedding space.
Exactly. And they carefully chose the scheduling function, this BTAT function, with its hyperparameters C and alpha, specifically to enforce a linear relationship between the time step $, and that embedding distance $1.
Linearity means predictability.
Precisely. It gives them that fine-grained, stable control over the refinement process, step by step. Crucial for long sequences.
Makes sense. So that handles the how much noise aspect with precision. But then there's the scale issue. Different resolutions, different video lengths. That's where the resolution-dependent timestep shifting comes in.
Right, because intuitively, a huge 4K video sequence needs a different kind of push, maybe a stronger initial perturbation than a small, low-res image preview. Applying the exact same noise schedule to both isn't optimal.
So they needed to adapt the path itself based on the input size.
Exactly. They introduced this time shift parameter, lambda. It basically modulates that linearized path we just talked about. The effective time tilde isn't just tellers, it's adjusted based on lambda.
And how does lambda change things practically?
Well, if you're dealing with high-resolution data, lots of tokens, they set lambda 11. This makes the relationship between effective time and actual time convex. It essentially front-loads the perturbation, giving it a stronger kick earlier on.
More aggressive refinement for complex data.
Yep. And for lower resolutions, they use lambda 11. That creates a concave relationship, softer, more gradual perturbations.
So it dynamically tunes the refinement intensity based on the data complexity.
Exactly. And they found this was critical for stable training when you're mixing different sequence lengths and resolutions, which you definitely want to do. It helps the model learn the sort of hierarchical structure in the data much better.
Okay, control and scaling handled. Now the third piece, flexibility, multitask learning, this asynchronous timestep scheduling. What was wrong with the old way? Just applying the same noise level to all frames.
It's just limiting. If every frame is at the exact same point in the noise-to-clean journey, it's harder for the model to learn certain conditional tasks, like generating video from a single starting image.
So URSA decouples this.
Completely. Instead of one noise level $T for the whole video, each frame gets its own independent noise level $T drawn randomly from 0 to 1.
So one frame might be mostly noise, while another frame in the same sequence could be almost clean during a single training step.
Precisely. This forces the model to learn how to reconstruct individual frames accurately, while also maintaining temporal coherence across frames that are at totally different stages of refinement.
And that's the magic that unifies all those tasks.
That's the key insight. Because the model learns to handle this mix of noise levels, it naturally becomes capable of things like text to video, starting from pure noise, image to video, where one frame is clean, the rest noisy, interpolation, where start and end are clean, middle is noisy, and extrapolation, where early frames are clean, later ones noisy.
Wow, okay. That's really efficient from a training perspective. One model handles it all.
It really is. They even show examples, I think, in the appendix, where they can condition on both the start and end frames and have the model generate the middle, hitting that future constraint.
Very cool. And just quickly, the backbone model they used.
Yeah, they built it on a pre-trained LLM Qwen3, but they added some important vision-specific enhancements like QK norm and an improved 3D rupee to better handle the spatiotemporal information in video. And for sampling, they kept it simple using the Euler solver, which is pretty efficient.
Good to know. All right, let's get to the payoff, the results. This is where URSA really seems to make its case. Not just better than other discrete models, but competitive with continuous ones.
That's the big headline for sure. That VBench score for text to video, 82.4, which is 1.7 billion parameters. That's really impressive.
Especially when you compare it to...
Right, models like OpenSora 2.0, which has something like 11 billion parameters, or VKTech 2.0, around 2 billion. URSA is matching or even beating some of these, particularly, and this is important, in the semantic aspects.
Meaning it understands the text prompt really well.
Exactly. Better text alignment, better adherence to what you actually ask for compared to several of these larger continuous models. It shows this iterative, discrete approach can really nail the understanding part.
Okay, so semantics are strong. What about image to video? How did that asynchronous scheduling pay off?
On VBench++ Pliba, they hit 86.2 overall, and the analysis showed that training with those decoupled noise levels really did boost the I2V generalization.
In what way?
It specifically excelled in metrics related to dynamics, things like camera control and how well it handled subject movement when conditioned on an initial frame. It actually outperformed some continuous models that were specifically designed for frame conditioning.
So that asynchronous training wasn't just for unifying tasks, it actually improved performance on specific conditional tasks too.
Seems so. It acts like a really effective form of diffusion conditioning for I2V.
Now, this next part, the ablation study on scaling, I think this is where things get really strategic for the field. They scale the model size up, right?
Yeah, from about 0.6 billion parameters up to 4 billion. And what they found is, well, it's a bit of a plot twist.
Go on.
Scaling the model size did significantly improve the semantic performance. Bigger model, better understanding of the prompt, better text alignment. That makes sense.
Okay, standard scaling behavior so far.
And this is the kicker. Scaling the model size did not lead to significant improvements in the overall generation quality. Things like image fidelity, visual realism. Those metrics stayed pretty flat beyond a certain point.
Wait, really? So making the transformer bigger didn't make the videos look significantly better?
Apparently not, beyond a certain point.
That's counterintuitive for diffusion models.
Yeah.
So if the LLM backbone isn't the bottleneck for visual quality, what is?
Their conclusion, and it seems pretty convincing, is that the bottleneck shifts. It's no longer the transformer's capacity, but the representation capacity of the discrete vision tokenizer itself, like the Cosmos or IBQ tokenizer they used.
So the LM can get better and better at understanding what to generate, but the final visual fidelity, how real it looks, is limited by how much detail those discrete tokens can actually represent in the first place.
That's the argument. You can scale the semantics with the LLM, but the pixel-level realism hits a ceiling imposed by the discrete codebook.
That is a huge insight. It basically says, if you want better-looking discrete video, maybe the next step isn't just throwing more billions of parameters at the transformer,
but investing in building better, higher fidelity, discrete vision tokenizers, ones that can capture finer details and textures in their codes.
It totally reframes where the research effort should go for improving discrete visual generation. Fascinating.
Absolutely. Shifts the focus from the generation model to the representation itself.
And one last quick technical bit from their tests, time-step conditioning, usually seen as pretty important in diffusion transformers.
Yeah, they tested adding explicit time-step embeddings or conditioning on time via text prompts. And they found, maybe surprisingly, it offered basically no measurable benefit after the first epoch of training with their uniform discrete setup.
No benefit. It could even hurt performance slightly.
A tiny bit, yeah, possibly due to increased variance in the embeddings. It suggests that for this specific iterative refinement approach, that explicit time conditioning might just not be necessary. The refinement process itself is enough.
Okay, so summing this all up, URSA comes along, takes discrete generation, and reframes it as iterative global refinement, much like continuous diffusion.
They introduce clever mechanisms like the linearized metric path for control and resolution-dependent timestep shifting for scaling.
Plus, that asynchronous scheduling gives it incredible multitask versatility from a single model.
And crucially, it achieves results that are genuinely competitive with, and sometimes exceed, state-of-the-art continuous models, especially on semantics. It validates the whole approach.
It really proves that iterative discrete methods are viable, scalable, and efficient for video.
Absolutely, and it gives us that incredibly important insight about the tokenizer potentially being the new bottleneck for visual fidelity, not the LLM size.
Which leads us perfectly to the final thought. If URSA shows semantic understanding scales well with the model, but visual quality hits a tokenizer limit, does the next major breakthrough in discrete visual AI depend less on building ever larger transformers and more on cracking the code for fundamentally better, higher fidelity, discrete visual representations? Is the tokenizer the real frontier now?
That feels like the million-dollar question this paper leaves us with. Where should the focus be? It might just be all about the tokens.